Today, we're cutting through the noise and the jargon of what has to be one of the world's most complex, heavy industrial machines, the modern drilling rig.
They really are. I mean, these structures, whether they're navigating the deep sea or set up on a desert plain, they're just incredible feats of cyber-physical engineering.
They are. And what's interesting and what a lot of people might overlook is that while the technology inside has completely transformed, the names of the major systems haven't really changed in decades.
That's right. We're still looking at the same 5 core elements: power, hoisting, rotary, circulation, and, control.
Exactly. So our listener today, a learner, they're familiar with those basics, but what they really want to know is how automation, how this seamless integration has revolutionized the performance of those systems.
Right. It's not just about what they do, but how well they do it.
So to guide our deep dive, we're going to use what I think is a perfect analogy. Think of a drilling rig as a high-performance athlete.
Oh, that's a great way to frame it. It helps immensely because it shows that a rig's success isn't just about one strong component, It's about how everything functions together in concert.
Precisely. So our mission today is to analyze those 5 systems, and we'll match them to the athlete: the metabolism, strength, motor skills, respiratory system, and the survival instincts.
And through that, we can highlight the specific, often hidden automation layers that really determine whether the rig just operates or if it truly performs at an elite level.
Okay, let's unpack this. We have to start with the foundation, right? The power system.
The metabolism.
The metabolism of the rig, the constant energy source. I mean, without stable quality energy, that athlete, they just can't perform any complex tasks without failing.
That's right. And historically, the power system was, let's say, a bit more straightforward. It was a brute force exercise.
Just keep the lights on.
Exactly. You had diesel or gas engines driving mechanical parts or maybe some DC generators. The goal was simply availability. Just keep the motors spinning.
But that model it's completely obsolete now. The modern rig is entirely different.
Oh, completely. It's electrically dense. You're often running on massive AC generators, all tied to a distribution grid that's just full of variable frequency drive, VFDs.
And those VFDs are everywhere, right?
Everywhere. They're on the motors for the drawworks, the mud pumps, the top drive, you name it. And this is where the complexity just explodes.
Okay.
The challenge shifts completely from power availability to power quality.
What do you mean by that?
Well, VFDs are what we call nonlinear loads. They pull power in these abrupt, non-sinusoidal waves, and this creates high levels of harmonics.
Harmonics, so like electrical distortions on the power grid.
Exactly. And this harmonic control, it sounds like an invisible threat, but it's a very serious one for the athlete's performance.
Yeah.
If the electricity looks fine on the surface, what's the real danger?
Yeah, what does that actually do?
The danger is insidious. If you don't filter and manage those harmonics, they cause these cascading issues. They introduce noise into the electrical system that can corrupt the sensitive signaling between the PLCs, the programmable logic controllers, and all the sensors.
I see.
And that leads to inconsistent torque delivery in the rotary system, false readings in the hoisting system. It just degrades the efficiency of everything.
So the power management system, the PMS, it's acting like the athlete's internal regulation, managing temperature and chemical balance.
Precisely. The PMS is an extremely sophisticated control system. It's governing generator synchronization, automatic sequencing. It's dynamically adjusting which generators are running based on predicted demand, not just the current load.
Who's looking ahead?
It has to. For instance, if the driller starts a high-load hoisting sequence, the PMS will proactively bring another generator online to prevent a voltage dip, a brownout, that could trigger an unnecessary trip or even damage equipment.
And the safety layer in all of this, it's there to make sure the core systems can always survive a potential dip like that.
Exactly. Safety means power integrity. We're not talking about simple fuses here. We're talking about highly redundant UPS-backed supplies for all safety-critical logic.
Especially the blowout preventer.
Especially the BOP control systems. That logic has to remain independent and protected even if the main power grid suffers a total catastrophic failure. The integrity of that power supply directly dictates the reliability of the automation that governs absolutely everything else.
Okay, so we've established the rig's vital energy, its metabolism.
Yeah.
Now let's talk about the physical heavy lifting, the hoisting system.
It is athletes' sheer strength and skeletal support.
Exactly. This system is responsible for handling these immense loads. the drill string, the casing.
And the components themselves are pretty straightforward. You've got the derrick, the crown and traveling blocks, the drilling line, and of course the drawworks.
Right, and traditionally the drawworks was this massive brake and clutch system. It required incredible dexterity and, I imagine, a lot of judgment from the driller to manage that load.
A huge amount of judgment. Now, though, it's a closed-loop electromechanical powerhouse. The drawworks are giant AC electric motors, and the driller is operating high-level control logic, guided by extremely precise load cells and encoders.
So they're getting feedback down to the pound.
Down to the pound. And the primary benefit of all this automation is actually mechanical fatigue reduction.
How so?
Well, every single time you start or stop a heavy load, you introduce shock and fatigue into the drilling line and the tubulars. So performance is defined by smoothness. Intelligent load sensing and acceleration control actively mitigate those shocks.
Can you give us a concrete example of how that automation translates into, say, efficiency or cost savings?
Sure. Think about anti-sway logic. When you're stacking pipe in the derrick, we call it tripping, the traveling block can start to swing, especially on a floating rig with wind or wave action.
Well, like a pendulum.
A massive, dangerous pendulum. So the automation calculates that pendulum effect and actively countermoves the motors to stabilize the load. This hugely reduces the risk of a collision with the derrick, or worse, with personnel.
And that's not just a safety feature.
Not at all. Reducing collision risk and line fatigue, that translates directly into higher uptime and lower maintenance costs.
It sounds like the hoisting system has different automated modes then, depending on what task it's doing.
Oh, absolutely. The control logic shifts dramatically. When you're tripping pipe, the system prioritizes fast, smooth movement. It's all about torque and speed control.
But when you're running casing?
When you're running heavy casing, the system prioritizes precise tensioning and extremely gentle set-down control. You need to make sure the casing shoes land softly without jarring the wellbore. The system applies the right type of strength for the specific athletic task at hand.
And the ultimate safety layer here, it must still be based on physical limits, regardless of how smart the automation is.
Yes, safety is always enforced by redundancy on physical parameters. We rely on independent upper and lower travel limits that will stop the motor no matter what the driller inputs.
Wait.
And extremely sensitive slack line detection to prevent the cable from unspooling, plus redundant emergency stop logic with controlled regenerative braking. The system has to know its own limits and never rely solely on human observation to prevent an overload.
Okay, so we've gone from general strength to the specialized athletic skill, the rotary system. This is that sophisticated motor skill used to do the real work cutting rock and steering the well.
And the shift here from the old rotary table and Kelly to the modern top drive system was, well, it was arguably the biggest revolution in drilling mechanics in the last century.
So the top drive sits above the wellbore, handling all the rotation from up there.
Right.
What's the major operational advantage of that for our rig athlete?
Time. It's all about time. The top drive lets the rig handle stands of pipe, that's 3 joints connected together, often 90 feet long, instead of just single joints.
So for every 90 feet you drill, you're making 1 connection instead of 3.
Exactly. You reduce the time needed for connections by 2/3, and maximizing the amount of time that bit is actually turning on the bottom. That's the absolute key to efficiency.
But the real optimization now, it comes from control, not just from speed.
Yeah.
It's not about brute force torque anymore.
Precisely. If our athlete is just swinging the club wildly, they're going to break the club and miss the ball. In drilling, uncontrolled torque leads to a phenomenon we call stick slip.
Stick slip.
The drill bit briefly sticks in the formation, the drill string above it winds up like a giant spring, and then the bit suddenly breaks free and spins violently fast.
I can imagine that just destroys the drill bit.
It destroys the expensive drill bit, it fatigues the pipe, and it severely reduces your rate of penetration. It's bad all around.
So how does automation defeat stick slip?
It uses some very sophisticated mitigation logic. You have high-frequency sensors on the top drive that detect the initial signature of that torsional vibration, that winding up.
And the automation doesn't wait for the driller to notice.
It instantly modulates the motor speed and torque, often by just a few RPMs, to dampen that vibration before the stick-slip cycle can even build up. It's this continuous, tiny adjustment to maintain a stable, efficient rate of penetration.
And the skill tools downhole, the ones doing the actual cutting and steering, they've evolved dramatically to match this surface control.
They certainly have. We mentioned the bottom hole assembly, the BHA. This is the specialized tool set at the bottom of the string. It has the bit collars, and increasingly very complex navigational equipment.
And the peak of that technology is the rotary steerable system, the RSS.
The RSS, yes.
What does that enable that the older motors couldn't?
Well, older directional drilling required something called slide drilling, where you'd have to stop rotating the whole drill string just to push the bit in a specific direction. It was slow.
Right.
The RSS lets the entire string rotate continuously, while internal mechanisms, guided by telemetry from the surface, actively push against the side of the well bore to steer the trajectory. It gives you superior hole cleaning, much faster drilling, and the ability to geosteer adjusting the well path in real time based on geological measurements, to stay within a really thin hydrocarbon layer, sometimes for miles horizontally. It's incredible precision.
Okay, let's transition now to the internal life support system for our athlete, the circulation system.
The respiratory and cooling system. This is what manages the massive volume of drilling mud.
And that drilling mud is often called the lifeblood of the well.
It is. Its functions are really threefold. First, it cools and lubricates the bit. Second, it carries all the rock cuttings back up to the surface. And third, and this is critical, it uses hydrostatic pressure to counterbalance the formation pressure,
Preventing fluids from the formation from getting into the wellbore.
Exactly. But the true value of the modern circulation system really is its diagnostic role. It is the earliest warning system the rig has.
The absolute first layer of defense.
It is. While you have the mud pumps, which are the mechanical muscle huge triplex or quintuplex pumps, the real intelligence is in the instrumentation. We rely on extremely precise flow meters and pit volume totalizers.
And those are monitoring the volume of fluid pumped down versus the volume that comes back to the surface.
To the gallon.
Why is that precise volume monitoring so vital?
Because the slightest discrepancy means trouble. I mean, the absolute slightest. If you're pumping a little bit less mud in than you're getting out.
That means something extra is coming out.
Yes. It suggests the well is taking a kick. Formation fluids, gas, or oil are flowing into the wellbore, and that is the precursor to a blowout.
And conversely.
Conversely, if you're getting less out than you're putting in, you have losses where the fluid is escaping into a fractured formation. That can weaken your pressure control.
So the automation here is all about anomaly detection. It's looking for those tiny changes.
Exactly. Trend analysis. The automation integrates pump sequencing and pressure data with those flow and volume measurements. It sets dynamic alarm thresholds.
So it's not just a simple high or low alarm.
No, because the allowable flow variation when you're actively drilling is much, much tighter than when you're, say, pulling pipe out of the hole, which naturally displaces mud. The system contextualizes the data, which is key to reducing nuisance alarms.
And if the data is all there in real time, what's the key operational risk for this system? What can go wrong?
The risk today, and we've seen this in multiple incident reviews, is alarm desensitization.
The crew just gets used to the noise.
Exactly. If the automation is poorly calibrated and it's constantly throwing non-critical alarms about minor flow fluctuations, the crew starts to ignore the system. Then, when a genuine critical flow imbalance occurs, the one real signal for an imminent kick, it gets lost. The human response fails because the system design failed them first.
And that brings us to the final, absolute non-negotiable layer, the well control system.
The ultimate survival instinct, the protective gear.
This exists for one reason and one reason only: to prevent that catastrophic failure, the uncontrolled release of formation fluids.
This is the system that transitions our athlete from high-performance mode to emergency survival mode in an instant. The hardware centerpiece is the blowout preventer stack, the BOP. It's what seals off the well.
And it has different components for doing that.
It does. It uses ram preventers, which can close off the pipe or even shear it entirely if needed, and annular preventers, which can seal around the pipe or just the open hole.
And the paradigm shift here has been massive, really driven by high-profile incidents. We've moved completely away from systems that rely on a human reacting under extreme stress.
The mandate for automation now is what we call deterministic response logic.
Deterministic response.
It means the system is designed to respond, not wait, based on pre-programmed verifiable conditions. Modern well control is continuously monitored, not just for function, but for its integrity. It's checking valve positions, hydraulic pressure, logic pathways, hundreds of times a second.
Can we get into that deterministic logic a bit? How is the shear ram, I mean, that's the ultimate last resort, how is it protected from human error?
The control logic is multi-layered. For a maximum intervention like activating the shear rams, the system requires concurrence from multiple independent sensors.
So it can't be just one false reading.
Never. It needs, for example, a combination of a rapid pit gain, high standpipe pressure, and gas detection, all meeting a preset severity threshold at the same time. On top of that, the activation system itself is protected by UPS power and redundancy. Subsea BOPs often have acoustic controls, allowing remote triggering via sound waves if all the electrical lines are severed.
It sounds like this system has to be completely independent of all other rig operations.
It absolutely must be. Its safety redundancy is non-negotiable. It has redundant control paths, redundant hydraulic supplies maintained by powerful accumulator banks, and complete independence from all non-essential systems lighting, HVAC, even the main hoisting controls.
So the design philosophy is that when every other system on the rig is failing,
The well control system must be guaranteed to function instantly.
Yep.
So if we synthesize this whole deep dive, I think the main takeaway is that the evolution of the drilling rig, it's not about new mechanics, it's about integrated intelligence.
right?
The 5 foundational systems, power, hoisting, rotary, circulation, and well control, they're now inseparable parts of a single cyber-physical machine.
And if we bring back our athletic analogy, a truly elite athlete isn't just strong or fast. Their performance comes from that integration. It's where the perfectly regulated metabolism
Managed by the power management system.
provides that clean, stable energy so the specialized motor skill, the rotary system, can execute this complex vibration-free steering.
All while the respiratory system, the circulation system, is providing instant contextualized feedback on the internal environment.
And that data integration is the key, isn't it?
Yeah.
Power quality affects the integrity of all the control logic, so poor electrical flow can degrade drilling performance and lead to stick slip.
And circulation data provides the early warning that immediately feeds critical automated decision-making for the well control system. Every system truly affects the next.
So the rigs that command the highest day rates, the ones that deliver the most reliable results, they're not just the ones with the newest steel.
Not at all. They are the systems of systems where the automation, the instrumentation, and those safety layers are engineered to communicate and cooperate flawlessly, optimizing performance under the most extreme conditions imaginable.
So here is our final provocative thought for you to chew on. We now understand that mastery of the modern drilling rig lies in these invisible layers: power management systems, closed-loop control, stick-slip mitigation logic, and these highly redundant deterministic safety paths. If these 5 fundamental systems are now so thoroughly instrumented and automated, where does the human element remain indispensable? What critical function is left that must remain under direct, non-automated human judgment? And what happens to human jobs and to safety when automation pushes even that final boundary?
That is the essential challenge for the industry's next decade.
Thank you for joining us for this deep dive into the mechanics and the revolutionary automation of modern drilling rigs.